Cathode-only X-rays is the idea of not using the anode side of the beam to develop an X-ray. It's Occam's razor. When you have the anode side of the beam in the picture equation, you have to overcompensate the cathode side to bring the anode side up to a minimum level. So let's institute Occam's razor. Don't use it. Just keep the body part of interest in the cathode side of the beam. It's very simple. Unfortunately, we have pre-processing in it. It's a computer program that has been developed to compensate or fix the picture for the anode heel effect. And you can't get around it. It's on every picture, every one. So you can't get around it. If you wind up taking a picture on the cathode side, it's destroyed via pre-processing, flat fielding. So we need a bypass to get around that. And we could lower, now remember, we can lower by 25 minimally up to 45%. That's huge. It's basically saying that you could reduce radiation exposure to the patient by half. And all you have to do is slide the body part into the cathode field. Now, I totally get that the field of view is small. It's half the picture, so it's going to be smaller than we're used to. We still do cervical, hands, feet, all of those in the cathode side. But why don't we just increase the field of view on the cathode? It's very simple. It's simple, but we got to do it the right way. Now, here is an X-ray beam. It starts here and it goes left to right. This is the cathode side. This is the anode side, and there's center. This, imagine if you would, is the IR plate, okay? Now, the image receptor sitting down here, this is how it's set up currently. And if you slide, so if you were trying to increase the field of view, you would not slide the IR down, okay? The reason you would not do that is because look at the distances between the beams. They grow as you go left to right. The way to increase without degrading the beam for the cathode is angle the beam. So now we center the cathode over the IR. So you would angle the bulb inside of the X-ray machine. So that way it's centering the cathode, doing away with the anode, centering the cathode in the field of view. This does not degrade or weaken the beam, because the idea is that the farther you walk away from center, the weaker the beam gets. And the reason for that is because the distance traveled is no longer straight. Shortest point between 2 points is a straight line. Okay, now when you start turning or when you start walking away, going left to right, the distance traveled and the distance between increases. So just turn the beam, just turn the bulb. Okay, now this side, the anode side, is the weak side. That's the side that's 25 to 45%. Let's just get rid of it. Stay with the cathode. And once you're centered there, left to right, it'll do the very same thing. It'll get a little weaker as we go to the ends, but there's no way around that because there just isn't. But that's how you would do. That's how you could increase field of view, reduce radiation exposure to the patient, and I know that everybody says this, and that is, it's a very low percentage of people. Well, the problem with that is that's true, but we're doing 326 I think it's 326 million right a year here in America. 326 million. 0.06 times 326 million. That's a lot of people. What is it? I got a number of a country, UK. It's 5 times smaller. According to Google, 700 people a year develop X-ray cancers. Okay, so that's a smaller country, 5 times smaller. So I'm just saying 3,500 people a year here in America are developing cancers from the X-ray. The X-ray is a necessary instrument in the healthcare industry. Got to have it. And you're going to, if you need one, you have to have it. Let's just make it safer. And I know the number at this 0.06 seems like so insignificant, but when you actually think about how many people that is, that's a lot of people, thousands of people. So this is more than worthy of lowering, because look, if we're this and we cut it in half, could we go from 3,500 people a year to 1,000, 1,500, 2,000? What if it's just one and it's you? See where I'm going? It's important. And look, you could keep existing equipment. All you'd have to do is just change the bulb, and look, if you change the bulb and you increase field of view, then you don't have to change all the procedures, the positionings, and so forth. You can keep it all the same. I don't know if we can get the full field of view in cathode. I'm just saying. But even if it weren't, we could increase field of view on cathode. I'm sorry if some people have to go back to school. I'm sorry if people have to relearn a few different things if it means helping and saving people from unnecessary cancers. It's what, in my opinion, it's the right thing to do. What is it? So we need a bypass. All equipment nowadays is made with pre-processing, and it's called flat fielding. No picture can be made without pre-processing. And the problem is that if you were to take a picture currently, cathode only, you try to do that experiment that I explained earlier or in a different video, it won't work. And the reason it won't work is because you take a picture on the cathode side, the machinery, the computer processing is going to degrade that picture reflective of what it's expecting higher levels of radiation. So then it's going to lighten a lighter picture, which then makes it unusable. What is it? So we need to be able to bypass pre-processing. Now remember, a computer is only as smart, program is only as smart as the person putting in the information. And at the time, that person's not an idiot. I'm not saying anything derogatory. I'm just saying at the time, that's how they fixed the anode heel effect, was by, recognizing dark areas to light areas due to high and low levels of radiation. And this is the fix, because now we can get a pretty picture. The problem was that that's not how it should have been fixed. It should have been fixed by increasing the field of view on the cathode side, lowering radiation to its minimal level, and then, ALARA, as low as reasonably achievable. And this is achievable. And all we'd have to do at this point is reprogram our existing equipment, and then we're changing the angle of the bulb. And it doesn't have to necessarily be the bulb. How about we don't want to do all that? Maybe we just, the bulb itself, we change the anode disc, to change the angle. Now you don't have to reconfigure anything in the machinery itself. It's just the bulb. There's a million ways to fix this. And we could get the cost down to nil, or, as low as possible. And then we could implement all this. But I don't know what to say other than I'd just like to help. And this is such an easy fix. Really, it's very simple. And why wasn't it discovered before? Like, but let's say with Madame Curie, people that are much smarter than me. Well, they didn't know. Madame Curie died of radiation poisoning because they didn't even know that, radiation caused, aplastic anemia and other types of radiation poisonings, cancers. They didn't know. What is it? And by the time they recognized the problem, well, it's, things started to change. But by the time, the anode Heal effect was somewhere in the 1950s. And right about that is when they brought in computer technology for the CT. And that's how it got fixed. But it's not right. It's just not right. I'm sorry. It's not. People at the time didn't have the information. And now we have the information, and this is the right thing to do. No one did anything bad. It's just that this is bad science. This is bad science. Now we know. So let's stop. We could fix this, and we could help. We could help a lot of people. And there's ways that we could get this done as economically as possible. Okay. Well, thank you for your time, and I hope that we can make impact in the future and we could implement some changes because it's very safe. Let me put it this way, if we were doing 3 x-rays a year, think about it, 0.06 by times 3, what's that, 0.18 or something like that, so nobody would have to get hurt. But when you're doing 300 plus million a year, the numbers are growing. And so hopefully we do the right thing. Okay. Thank you very much for your time.